This is our last video, arc length. So if you remember our arc length formula from here, and so we're going to do a quick little change again of our variables. So we have dx. We remember before on the previous video, we get x prime of t dt using substitution. And then now we can distribute that x prime in. So if you put a square and a square root around it, you end up with this. So it just gets distributed in. And then we rewrite it, do a little bit of changing of variables, and there we go. So what it really is just we're taking the derivative of our x with respect to t, the derivative of our y with respect to t, squaring them both, square rooting, and then doing the integral from our starting t to our finishing t. So let's try one. So there's our graph, and we're going from 1 to 4. So what we're looking for is that arc length. So how far is this little dot traveling from x equals 1 to x equals 4? So from t equals 0 to t equals 1. So how far did that little dot travel? So we go by our formula. And so we're going to take and square the derivative of x, square the derivative of y, and then square root it. So dx dt equals 6t, dy dt equals 6t squared. And then we need to square it. So we end up with 36t squared let's try that one again. 6t squared. So this is 36t to the 4th. All right, so now we have our dx dt squared, our dy dt squared, and now we just need to add them together and put a square root around it. So I'm going to actually shrink this a bit. So we get square root of 36t squared plus 36t to the 4th. And you can see that we can actually factor out a 36 and a t squared. Like that. And so this would be 1 plus t squared, just like that. So we end up with 6t square root of 1 plus t squared. So it's very similar to like we did with arc length of the regular functions, where we would take the derivative, add 1, and then square root it and simplify. And so we get all that done, and now we can do our integral. So we're going from 0 to 1 for our t of 6t square root of 1 plus t squared dt. So there's our setup, and now we just take our integral. So this is a nice u substitution one. And so du is equal to 2t dt. And so you can see our 6t would just be made up of 3 times 2. So I'm going to take out the 3. And then we need to now change our interval. It's not from 0 to 1 anymore because that's for t. We need it for u. So again, that would be, here I'm going to put it up there. This is 3 times 2t. And then that way we can just say 2t dt is our du. So we would end up with the square root of u du. So 2t dt, that's du, and 1 plus t squared is u. All right, so now if I plug 0 in, I would get 1. And if I plug 1 in for t, I would get 2. Okay, so this is u to the 1/2, so we would get u to the 3/2, 2/3 times 3. Let me move that down a bit. 2 and 1. So this is 2, and then 2 to the 3/2 minus 2 times, so I'm just canceling the 3 already, 1 to the 3/2. And so this is going to be 3 sets of 2. So again, you're going to simplify that radical. Here, this is this. It's 2 cubed. So we can take out 2, which makes 1. So this would be 2 rad 2. And there's already a 2 sitting in front of it. So that would be 4 radical 2 minus 2. And you can keep factoring and say 2 radical 2 minus 1, your choice. All right, and just like all the other integrals we've done, just like our previous arc length problems, you want to take and plug this into your calculator, and not like the simplified form. So the derivative's nice and quick. You're not going to make a mistake there. At least you shouldn't be. So we plug it in 0 to 1, square root, and then it's our 6t squared and our 6t squared, right? And then we find out we get that. That's perfect. And then our answer, which is 4 rad 2 minus 2, and you see they match. So we know we're good. All right, let's try the second one now. So same exact thing. We're going to find our dx dt first. So that's 2 sine theta cosine theta because it requires chain rule. And then it's d theta. D theta. Very good now. All right. That's 2 cosine theta and then negative sine theta. And then now we have to square them. So dx d theta squared would be 4 sine squared theta cosine squared theta. And then dy d theta squared would be 4. Let's put them in order, the same order. So we'd have sine squared because the negative is just going to turn positive. Okay, now we have to add these together. So we end up with 4 plus 4, which is 8. They're both the same term, sine squared, cosine squared. So we have that. And then now we square root the both of them. So we have 2 rad 2. Now here's the tricky part. When you square and square root something, you need to make sure you put it in absolute values. So you have sine theta, cosine theta, absolute value like that. And now I see the 2 sine theta is 2 sine theta cosine theta. We can actually make that into one term. That's nicer. So we can use our double angle identity. So sine of 2 theta is 2 sine theta cosine theta. Now you could also use u substitution with u equals sine theta and everything, but this is just a lot nicer. Now, here's the thing. When you deal with trig functions, you get a lot of repetition when you're squaring them. So if you just think about a normal circle, just a normal circle, as we go through it, that arc length is going to be the same as that arc length, which is the same as that arc length. I'm out of colors now. Let's go back to green, which is the same as that arc length. So it's 4 of them. So at pi over 2, once you find that arc length, you can just quadruple it. So when you get things like absolute values here, this is the graph that we end up getting. So you can see when we're trying to find the area under the curve, you can't just throw the absolute values away because it's all positive. We're above, we're above, we're above, we're above. If you would think about it without it, the negative values are going to appear and it's just going to zero out if you don't include them. So the best thing to do is to just think about your period. We're going from 0 to 2 pi. So that means we can just go from 0 to pi over 2 and then by symmetry, quadruple it. You can even see with our parametric equation, when I go from 0, you see I have it set from 0 to 2 pi of our function here. When I hit play, watch what it does. 1, 2, 3, 4. So it's going to go through it 4 times. If I change the period on these problems, and I put a 2, now it's going to go 4 times as fast. The period here would be just pi. And so in 2 pi, we're going to go through the circle 2 times. So watch 1, 2, 3, 4, 5, 6, 7, 8. Twice as fast. And if I make it a 0.25, it's going to go 4 times as slow only 1 time. And so if I were to make it 3 times, isn't this interesting? Pretty cool, right? It would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because it's going to hit the pi over 2 12 times, right? So backwards and forward. So when we're looking at our graph for this problem, we have to go from 0 to 2 pi. It means its period is 2 pi, which means it's going to go through each quadrant, right? And then have that same symmetry where everything gets turned positive 4 times. So we can't just throw away these. So if we're going to go from 0 to 2 pi square root of 2 of sine 2 theta, because remember we're still doing arc length here. You have to break it up. So you can go from 0 to pi over 2, and then from pi over 2. So basically we're going to go from 0 to pi over 2, and then pi over 2 to pi, and then pi to 3 pi over 2, and then 3 pi over 2, to 2 pi. So there's 4 of them. That's 1, 2, 3, 4, right? So we have 4 rad 2, and then we go 0 to pi over 2, and we can throw away the absolute value by symmetry. So we're just calculating one of each of those little humps. Okay. So now when we do this, we do 4 radical 2, and then a half. Oop, there's a negative in there. Negative, I'll just put it here, cosine 2 theta, pi over 2, and 0. So we end up with 2 rad 2 with a negative cosine 2 theta. So we'll just plug it in now. Let's try this again. Bracket cosine. Pi over 2 plugged in is just going to be pi minus cosine of 0. And so this is negative 1 minus 1. So we end up with 2, 4 rad 2 for our arc length. So you want to think about it breaking it up. So if this had been a 2 here, right, then this is going to appear 8 times. And so you'd have to put an 8 here and go from 0 to pi over 4. Okay. So now what we just found was the total distance traveled by the particle, not the length of the curve. Because our curve, let's change this back, has not changed no matter what I did with the period, right? It's still the same thing. Our curve is just from here to here. That's the length of our curve. So if it goes through it 1, 2, 3, 4 times, then I think you already know what we need to do. That was the total distance, which is 4 rad 2. So our length would be 1/4 times 4 radical 2, which is rad 2. So when you get to these problems with the absolute values, the best thing to do is to just graph it. And to take a look at it, it will tell you what your repetition is, and use symmetry when you do that. So like I said, if I were to put a 2 here and a 2 here, then within a 2 pi, it's going to appear 1, 2, 3, 4, 5, 6, 7, 8 times like we knew. And it's at pi over 4 that you're going to have to go from. So from 0 to pi over 4, and then multiply it by 8. So the arc length is going to give us the entire distance. But to find the actual length of the curve with these functions that repeat, that keep circling around, you have to use a little bit of logic to find the actual arc length.